Hello. In this video, we are going to use the technique of Euler's method to solve a differential equation numerically. So oftentimes we have a differential equation, dx dt is equal to v of t, that we can't solve using paper and pencil. We can't find the actual solution to it, so we need to find a numerical solution. So Euler's method is a way of finding a numerical solution to a differential equation, like this. So the first thing we do is we essentially do calculus in reverse. So we're going to turn that dx dt, that derivative, into delta x over delta t. So with finite differences, delta x and delta t, still equal to v of t. Well, let's isolate delta x here and multiply delta t on both sides. So I have delta x is equal to v of t delta t. And then delta x is the difference x sub f minus x sub I between 2 points. So let me just write that out and put x sub f on the left-hand side and x sub I on the right-hand side. So I have x sub f is equal to xi plus v of t delta t. So this is transforming my original differential equation into something that allows me to find the solution x sub f at the end of some time interval of size delta t. So in a cartoon, what it looks like is this. We have some initial condition, t sub 0 and x sub 0, the initial time, and then the solution, the x at that initial time. And we use that to calculate the initial slope, v, at t sub 0. So that tells me the slope of my solution at the initial time, t sub 0. I use that slope to calculate x1. So I just use that x1 is equal to x0 plus v at t0 times delta t. So that initial slope tells me where my new position, x1, or my new solution, x1, should be. And then t1 is just the original time, t0, plus delta t. So I just have this time interval of size delta t, and I'm stepping forward to the next point just given by the linear approximation, taking the slope at that initial point. Well, I can do that now at my point x1 to find the next point. So I can keep going further and further out. So the next point, x2, is given by taking the slope at x1. For instance, maybe it's flat here, as shown here, and then that will tell me where x2 is. So I just move out to the right a distance, the solution x1 is equal to v of t1 times delta t, and then I move horizontally, t2 is equal to t1 plus delta t. So I just move another interval delta t, and so on and so forth. And so by doing this for each of the time intervals, and several different time intervals, I can string together a numerical solution to my differential equation. And so this is the Euler's method solution to the differential equation. Now, as with most things in calculus, if you make delta t smaller, you'll get a more accurate solution. And in particular, if you have delta t fairly large, you might expect your solution to be pretty far off. So for example here, I'm just showing an example of what this might look like. The actual solution and the Euler solution are a little bit off, and in order to make those come closer together, then I would need to make delta t smaller and smaller in order to get the actual and the Euler solution to be pretty close to each other. Let's look at an example of how we might do this and how we would make this calculation, say, by hand. So let's take an example of dx dt is equal to 5 times t, with an initial condition x at t is equal to 0 is itself equal to 0. So I have t0 is equal to 0 and x0 is equal to 0. Okay, so this 5t is my v of t, and I'm going to use that anytime I see v evaluated at any particular time. So in particular, looking at the first point, x1, I'm going to be evaluating v at t0. So this right-hand side for x1 really looks like x1 is equal to x0 plus 5 times t0 times delta t. Well, let's set up a table to do this calculation. So in this table, I'm going to take delta t is equal to 0.5 so that I can actually do some calculations. And the first line of this table is the t0. So t0 is equal to 0, x0 is equal to 0. In order to find the next line in the table, I need to calculate x1, which is x0 plus 5 times t0 times delta t. Well, x0 is 0. Then I have 5 times t0. Well, t0 itself is also 0 times delta t, which is 0.5. Okay, we can simplify this, but let's just hold on to it for a second, because I want to do now the second line for t as well. So the second line for t as well is that t1 is t0 plus delta t. So I just take t0, which was 0, plus delta t, which is 0.5, and that gives me t1. Okay, now let's simplify these a little bit more. So then I have 0.5 and 0 for this line of the calculation. Okay, so that gave me the t1 and x1 line of the calculation. Now let's go on to the next step, finding x2 and t2. For x2 and t2, I'm again going to take my v of t, which is 5 times t, and I'm going to plug it in for v evaluated at t1 now. So that's telling me the slope evaluated at point t1. So x2 in this case is going to be x1 plus 5 times t1 times delta t. Well, I can read those off. x1 is still 0, plus 5 times t1. T1 now is not 0. T1 actually is the t line from right above this one, so that's 0.5, and then times delta t, which is also 0.5 in this case. I can do a similar calculation as I did before for t2. T2 is t1 plus delta t. T1 itself is 0.5 plus another 0.5. And so for this line, I get 1 for t2 and 1.25 for x2. And so on and so forth. So I could keep doing this calculation by hand for several different more points. And if I wanted a more accurate solution, I'd have to go back to the very beginning and choose a smaller delta t and do all those calculations by hand. Now, naturally, we don't want to do this by hand. This is something that a computer is really good at, doing these types of calculations. And so in another video, we're going to look at how we can ask a computer to do these calculations for us.